So with the last method that we used to solve this problem, we had some issues with restraints on the time change that we could use for our temperature profile. So now I'm going to go ahead and show a second method that we can use called the Crank-Nicholson method that will get rid of this time constraint, so we'll be able to use any value for delta t. So this method is called the Crank-Nicholson method, and again I'm going to go ahead and start with the heat diffusion equation for this problem. So we have the derivative of temperature with respect to time, and that's equal to alpha times the second derivative of temperature with respect to x. And so for this method, it'll be pretty similar to our last one where we make approximations for both our derivatives, but they'll be a little bit more accurate, especially for this one, and hopefully we won't get any constraints on the R value that we can use. So to estimate this derivative, it's actually going to be identical to the last method. And so it's just going to be the temperature at j plus 1, or the temperature at j, or increment j, at time n plus 1, minus the temperature at j at time n, over delta t. And then on the right side, we have alpha. And now for this increment, for our last method, we used just a single time n to estimate this derivative. Now we're going to estimate it at the first time n, and then at the second time of n plus 1, and then take an average of those two, and it'll give us a more accurate estimation for this derivative. So what this is going to look like is it's going to be the same estimation we used for the first method. So it's going to be t of j plus 1 at n minus 2 tj at n plus t at j minus 1 at n over delta x squared. And now we need to do the same thing for the next time increment. So it's going to be t j plus 1 at n plus 1 now, minus 2 tj at n plus 1 plus tj minus 1 at n plus 1. And this is still over delta x squared. And now since we're taking the average of these, we just need to divide by 2. And so from here, we know all the temperatures at the time increment of n, because that's our current time, but we're looking for all the time, or the temperatures at the next time increment of n plus 1. So we need to isolate these terms on one side of the equation and have our known terms on the other side, and then we'll be able to solve this. So to do that, I'm just going to simplify this a little bit. I'm going to multiply delta t over and factor out our delta x squared. So the right side of the equation is going to look like this. Same thing, it's just no longer divided by delta t. And it's going to be equal to alpha over 2. We multiply delta t over, and then I'm going to factor out delta x squared. And so the rest of these terms in the parentheses just stay the same. And so now from here, we can go ahead and move our unknown temperatures to the left side and the known temperatures to the right side of the equation. Before we do that, kind of similar to our last method, we have this coefficient out front. Most textbooks still call it R, but to kind of eliminate confusion so we don't mix it up with the last method I used, I'm going to call this U. And so now we can go ahead and start moving these over. So we're going to have moving this term here over. we're going to have u times this term subtracted to the other side. So it's going to be negative u times t at j plus 1 and n plus 1. And now I'm going to go ahead and move this term over and combine it with this one. And so it's going to be u times negative 2. We'll add it over. So this is just going to be plus 1 from this term over here, plus 2u from the coefficient on this term, times tj at n plus 1. And then our last term, we're going to move this term over. So it's going to be negative since we're subtracting it to the other side, and then multiplying by u. So negative u times tj minus 1 at n plus 1. And then on the right side, these are going to be all of our known temperatures. And so we'll have u times tj plus 1 at n plus 1 from this term. We'll add it over to the other side, minus 2u from this term, times tj at n, and then we have this term that's just left. Remember to multiply it by u. So it'll be u times tj minus 1 at n. And so now from here, we'll have equations for the increment of j equals 1 all the way to the increment of j equals n minus 1. And so we're going to have loads of different equations at different position increments. And so we'll actually be able to write these as a matrix and solve them for our unknown temperatures. And so what this looks like is we're going to have a matrix of unknowns. And this is going to be all of our temperatures at the next time. And so t is going to equal n plus 1 times our time increment. And so, like I said, we know the temperature at t of 0. It's held constant, so it doesn't depend on time. We know the temperature at the increment of t at n, which is all the way on the right side of the bar. And that's held constant at 80, so we're really only worried about the innermost temperatures. So we'll start this at t of 1, t of 2, t of 3, all the way down to t at big N minus 1. So now we just need to plug in the left side of our equation. I'm going to go ahead and start with the increment of j equals 2. And so for that, we're going to have negative u times the previous temperature. And then we'll have 1 plus 2u times the current temperature, which, since we're at j equals 2, is just T2. And then we're going to have, again, negative u times the next increment, T of 3. And then the rest of these in the matrix are just going to be 0, because the temperature at 2 doesn't depend on T of 4 on. And so we can go ahead and write it for the increment of j equals 3. So we're going to have a 0 on the far left in our matrix. And then we're going to have negative u times temperature when j equals 2. Then we have 1 plus 2u times T3. And then we again have negative u times T4. And so I can keep writing these. If we write it for another line, we're going to have 2 zeros in the matrix, negative u times T3, 1 plus 2u times T of 4, and then negative u times T of 5, which would be the next temperature. And then, like I said, the rest of these are just filled with zeros. So now for T of 1, Since t of 0 is constant, we do not need to include that first term. And so the very first value in this matrix is just going to be 1 plus 2u multiplied by the t1, and then we'll have negative u multiplied by the next increment. And so this matrix has 3 diagonals in it, and we'll actually use that later on when we move to Python to solve this problem. Now we need to write in the right-hand side of our equation. And all of these temperatures are our known temperatures, and they're at the time of n times our time increment. So all of these in this side are going to be known. Again, I'm going to start with t of 2. And so for this, we're going to have u times the previous time. So it'll be u times t1 plus 1 minus 2u times the current increment. So it'll be 1 minus 2u times t2, since we're at j equals 2. And then again, we're going to have u times the next increment, which, since we're at t of j equals 2, is t3. Now I can go ahead and write this for the next one. It's going to be u times t2, which is the previous increment, plus 1 minus 2u times the current one, which is t3 for this line, and then u times the next increment, which is t4. And so this line will be the same for all of these lines in the matrices, except for the first and last one, because we know those temperatures on the edges. And so at t equals 1, this term, the temperature at 0 at time n is 50, and since it doesn't depend on time, this term over here is also going to be the same. So we can move it over to the right-hand side of our equation. And so what this first line is going to look like is, I think I made a mistake here. I switched these. We have it written out as our j plus 1 term first. And so for this line, it should be t2, and this line should be t1. Same thing with here. We just have to switch these. This will be t4. This should be t3. This is t4, and this one is t2. And so now for this line, we'll have u times the next time increment, which is t2, plus 1 minus 2u times the increment that we're at, which is t1. And then since we moved this term over to the other side of the equation, and these are both the same value, we're just going to have 2 times u at t0. And so for the last line, something similar is going to happen. We'll know the temperature at the next increment, because when we're at t equals n minus 1, the next increment is t at big N, so it'll be all the way on the right side, and that is held at a constant 80. So we can move this term over, and so the first term on this side of the matrix is just, again, it's going to be 2 times u times tn, and then the rest is just going to be the same. We'll still have 1 minus 2u times the current increment that we're at, which is t of n minus 1, and then plus u of the previous increment, which is just t of n minus 2. And so now that we have all of this written out, we'll be able to move to Python and use a method called solve banded to solve this banded matrix, since we have these diagonals on the left side of our matrix equation. All right, so now that we have the equation that we need to solve this problem using the Crank-Nicholson method, I'm going to go ahead and code it in Python. So the first thing that we're going to do is just define our constants. So the temperature that the bar is initially at is 20 degrees. The left side of the bar is still going to be held at 50, and the right side of the bar is still going to be held at 80. Now from here, we need to define alpha, which I'm going to use the same alpha value as our last method, dx, which we set to 1 when we split up the bar, and then dt, which right now I'm just going to leave it at 1, because with this method, we shouldn't be running into the same issue as the last one whenever we set dt to anything over 1/2. So now from here, we can calculate our value of u, which is going to be alpha times dt divided by 2 divided by dx squared. So now from here, I'm just going to go ahead and create the temperature profile of our bar. So we still have 20 segments, so n is equal to 20. And then we'll use the function np full to make an array of size n and fill it with the initial temperature. Then we'll set the first element in our temperature array to be the left temperature that we're holding steady, and then we'll do the last temperature in the list and set it equal to the temperature of the right side of the bar that we're also holding steady. So now I'm just going to double check that everything looks right. And then from here, we can start to code this equation in. So the function that we're going to use is solve banded, and I went ahead and added it into our import statement at the top of our code. And what this function looks like is it takes in, or it solves an equation ax equals b, assuming that A is a banded matrix. So for this problem, this left side matrix will be our banded matrix because we have those 3 bands of diagonals. So we need to supply the lower and upper number of diagonals. Then we need to supply AB, which is our banded matrix in this form. And so the upper band will have no value in the top left and have all of our values from the second index on. Our middle diagonal will be full, and in this case, it'll be 1 plus 2u. And then our lower diagonal will start at the beginning of the list and have an empty value in the very far right. So to start this, we need to create our matrix that's going to be banded, and I'm just going to call it A banded. And to start, I'm going to fill it with zeros, and we'll give it 3 rows because we have 3 bands, and make it a size of n minus 2. Because for this matrix, we're not including the index of t at 0 and t at n, so the matrix will be 2 columns shorter. And then from here, we need to set the first row in the column to our band of negative u. So looking back here, we start at the second index of it, and so it will be from 1 all the way to the end, and this is just equal to negative u. Now for the second row, that's going to be our full diagonal, and so we will need to fill all columns, and that is just the value over here of 1 plus 2 times u. And now the third row in this matrix is going to be the lower diagonal, and so we'll fill it with the values starting from the very left and leave a space at the end. So we'll use all columns and exclude the last one, and this is also equal to negative u. So now if we look at A banded, it has a blank value in the start, and then our upper diagonal, which is all negative u. The middle row is our middle diagonal, which is all 1 plus 2 times u. And then we have the lower diagonal, which is all negative u, except for the blank, or the last value. So this looks right. From here, we can go ahead and form our right side of the equation, which I'm going to call b. So basically, all we have to do is just plug in these values. And so we're going to have u times the temperature at the next index. So since we're excluding the very ends, the next index in this case is going to be 2. So 2 to the end. And then we'll have the coefficient 1 minus 2 times u. And this will just be our temperatures at the current index. And then we will have u times our temperatures at the previous index, which will be from the very beginning of our list to the second to last one. And now, like I said, while we were working on the whiteboard, our top row and bottom row in this matrix need to be adjusted because we have that extra value. And so to do that, I'm going to adjust the top row first. So we'll set the very top row of b equal to itself plus the extra term of u times our first temperature. And then same thing for the last one. We need to adjust it by adding u times the second or the last temperature of our bar in the blocks of our bar. And so now from here, we are ready to use solve banded. So we need to supply the number of lower and the number of upper diagonals. So in this case, we just have one above and one below. We need to supply our banded matrix, and then we need to supply the right side of the equation. And now, so these values are the values of our temperatures from blocks 1 to 19 at the next time. And so to continue to do this and kind of get the temperature profile over time, we need to set this equal to our new temperatures and then run it through an if statement. So I'm just going to go ahead and copy and paste this up to the next line and create the for loop that we need. And so we'll run from time 1 to 500. I need to make sure that I index these in to the loop. And then from here, I'm just going to go ahead and grab the code that we used to graph our last method and kind of implement it into this code. So we first used this. To create our first graph. And then we used this code here to create each graph after we run through our loop. So since we're running the simulation for a little longer, I'm going to go ahead and change this to graph every 5 iteration. And so now I'm going to go ahead and run all of our code. And there's the temperature profile using this method. So now if you see, DT is set at 1, which is already out of the bounds of our last one, but we can even increase this more. We'll get less graphs for a temperature profile, but it still works and it's still accurate. And then we can even go lower to take smaller steps down to, let's say, 0.02 or 0.2. And if we run it again, we still get an accurate temperature profile.